Now, okay, so this is lecture 32 of Calc 2, virtual learning as we dodge the Ronivirus. I am not at the beach, although I wish I were. Okay, so let's get this situated. What have we been talking about? So we've been talking about some complicated things. So let's sort of set the stage. So last class we stated some important results about what are called geometric series. So for example, we know the following. We know that 1/2 plus 1/4 plus 1/8. We know that this infinite series is geometric. And we also know that it sums to the number 1. We actually proved this 2 classes ago. And we stated the general result about the series in general on Tuesday. So what is important about this? Well, what's important is the following. And this is an observation that you might want to make. So my computer is on fire. I think my computer's going to die running all these virtual lectures. Got your processor going crazy. So what is an observation? Note that the terms are quote unquote getting smaller. So I hope you use your context clues, what I mean by that. But if you look at this series, if you look at this quote unquote infinite sum, excuse me, what you'll notice is as you count or as you look, as you read left to right, the terms are becoming smaller and smaller. So let's look at the following from a different perspective, a more general perspective. Similarly, if 1 is larger than r, and r is greater than -1, we have the following. We have 1 plus r squared plus r cubed. We know that this guy is the geometric series, and we know it's equal to 1 divided by 1 minus r. So once again, what I'd like you to notice is as we read left to right, the terms are quote unquote shrinking to 0. I mean, think about it. If you take a number like 1/2, or you take any number between -1 and 1, if you take the limit as the power goes to infinity, you get 0. I mean, that is a consequence of L'Hopital's rule from Calc 1. So more specifically, we can think of it like this. The limit as n goes to infinity of r to the n, this equals 0 when r is between -1 and 1. So if you don't remember this, we did this in Calc 1. But you can use L'Hopital to show this. I'm not going to go through it, but if you want, you could. But look, a better way to do this, a better way to show it is to just convince yourself. Take any number and raise it to a large power. If that number is between -1 and 1, it's going to be close to 0. So why do I even bring this up? Well, the reason we bring it up is because what we need to know is we need to know, is this something special to geometric series, or is this something that we should expect all series to have? So that is a question we might ask ourselves. I'm sure you spent your whole night last night fighting sleep over this thought. And so the question would be, is this unique to geometric series? Boom, 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 boom. And the answer is no. And if things stop popping up on my computer. Okay, so it turns out, as you might expect, a condition for any series to converge is that the terms as we read left to right quote unquote go to 0. So we're going to state this specifically in a second, but I want you to think about this from an intuitive standpoint. If I tell you you're going to keep adding and adding and adding, and it's going to approach another number, it doesn't make sense for that unless the numbers you're adding towards the end are all essentially nothing, if they're 0. I mean, again, think about writing some pattern down that you're going to add up. What is the only conceivable way that pattern would make sense to have a sum? Well, if you ponder that for some time, you're likely to come to the conclusion that it has to look like those series we've been studying, that the terms, as you read from left to right, I hope you're not me, that the terms are going to 0. And again, we'll set that specifically in a second, but let's go back here. What do I mean? If you read this equation from left to right, these numbers are to a power. Well, what is happening? R cubed is something, then R to the 4th, R to the 5th. If R is between -1 and 1, then R to a very large power is going to be essentially 0. If you don't believe me, I mean, go to a calculator. Let's go and share a calculator. We'll take, I don't know, give me some web page. Give me a web page. Where are you web pages? All right, so if if you go to this, if I just take the number, let's say 0.3, that's between -1 and 1, and I raise it to like the 243rd power. Well, Google tells me that that number is like 8.7 times 10 to the -128. That is 0. That is an extremely small number. So hopefully you get the point that I am trying to make. I don't know that you are, but hopefully with some thought, it'll make sense. So let's go back to our whiteboard. Does anybody have a question? Okay, so how do we say this specifically? So this is very, very important. We're going to use this. So before stating the precise theorem, note we are now talking about a series in general. So what does that mean? We're talking about something that looks like this. K goes from, say, 1 to infinity or 0 to infinity of a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So we are not making any assumptions. This is not, so to be very specific, this is not necessarily geometric. So you have to keep this in mind. This, no one says that it's number squared plus number cubed plus number to the 4th plus number to the 5th. That's not necessarily what this is. These a sub 1s, a sub 2s, a sub 3s, they can be anything. So let me explain that one more time so we're very clear. So for example, if the kth term is 1 over k, what do you have? Well, you have k goes from 1 to infinity of 1 over k. And what does this mean? Well, when k is 1, you get 1 plus a half plus a third plus a fourth plus a fifth. And of course, this pattern continues and continues. If a sub k equals k over k factorial, you remember this guy? Well, let's not say k fact. Let's do it like this. Let's be a little more unique. If a sub k equals, say, 1 over k factorial, what does the series look like? Well, you would have this. You would have 1 plus 1/2 plus 1/6 plus 4 factorial is 24. 5 factorial is 120. So as only I could scream and yell at you, these ain't geometric. And we are using ain't because why not? We're in quarantine with virtual learning, and we are going to use the word ain't. Ha! Okay, does anybody have a question about this? I'm not saying anything about these series. I didn't say they converge or diverge. All I'm saying is here are two examples of series that are not geometric. Because right now, the only series that we know anything about are geometric. We want to be able to analyze these creatures.
So because their sums aren't going towards zero?
No. Well, no, there's sums. No. Slow down. Their sums aren't going anywhere. Even geometric, the sum ain't going towards zero. The terms in the sum were going to zero. But look at both of these. If you look at the top one, you get 1/4 and then 1/5, then 1/6. Where are those terms going? They're clearly going to zero.
Yeah.
I mean, what's the 100th term in that sum? It's 1 over 100. What's the 600th term? It's 1 over 600.
But because it's not between -1 and 1?
No, these aren't geometric. You shouldn't be thinking about -1 and 1 at all right now. There's nothing geometric about these. These are different types of a series. Just like, you know, if you want, this is an electronic pen, not to be confused with a regular pen. These are series, not to be confused with geometric series. They're two different types.
Okay.
What we want to know is we want to develop, hopefully, similar ways of analyzing these guys, just like we analyzed the geometric ones. So let's make a point about that, because it's going to be worth our time. Note, in both examples, the terms are going to zero. And so what do I mean by that? We'll take it. What's the limit as k goes to infinity of 1 over k? Well, it's clearly 0. And what's the limit as k goes to infinity of 1 over k factorial? Well, that's going to 0 even faster. This is, again, don't forget, if you're forgetting about this factorial thing, let's not forget that. That's going to be very useful going forward. So when we write k factorial, that means k times k minus 1 all the way down to 3 times 2 times 1. This is called a factorial. Okay, so does anybody have a question? So I said this at the end of class on Tuesday, and we have to remind you of this again. So, oh yeah. Did you say back one?
Yeah.
Yes, please.
This one or one more?
This one.
Yep. Okay, does anybody have a question about this before we move on? Everybody good? Speak now. All right. Okay, so where are we going? What's the point of this? Well, the point is as follows. So we will soon see an interesting fact. And that is this series the 1 over k guy, which is 1 plus 1/2 plus 1/3, this guy diverges. We'll show you. Notice I say we will soon see. While this guy one over k factorial, which was 1 plus 1/2 plus 1/6, this guy converges. So this is very counterintuitive on your brains. What this means is if you spent the rest of your life adding up the top ones, you would never end. You would never end. If you went to a calculator and said 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, you would never see a pattern. However, if you went downstairs and did 1 plus 1/2 plus 1/6 plus 1/24, you would see a pattern. So let's write that down. So let's put it in what we call layman's terms, or in baby language. Let me write it. I don't want to write a limit here. So let me be very specific. You would never see a pattern with trying to sum this guy. But you will with this. So let me be very clear. Let me even be more specific. Let me take my eraser and erase this right here. So let me get as specific as I can. You will never see a pattern with trying to sum this partial sum, but you will with this. So that is very interesting. And again, if we had all the time in the world, I would go to the computer and tell you to do that, but you could do it for yourself. You could just go, you know, if I went to share something, I don't want to erase this quite yet. Let's see if you guys have any questions. Does anybody have a question about this before I share? All right. So if I share my web page, so suppose I just started adding this up, like 1 plus 1/2, oh boy, plus 1/3, plus 1/4. So say I add the first 4 of them up, I get 2.08. But if I add the next one, I get 2.28. And then if I add the next one, I get 2.45. So that doesn't necessarily mean bad news, but if you kept doing this for large numbers, you're going to see there's no pattern. However, if I look at the other guy, if I say 1 plus 1/2 plus 1/6, then I get, if I look at that partial sum, I get 1.667. Now, if I add the next guy, which is 1 divided by the next guy would be 24. Why did it do that? Do I need to do this? Now I get 1.7. So now I get 1.7. Let's add the next guy. What's the next guy? The next guy is 1 divided by 120. And bow, I see a pattern. Now I had 1.72 in a row. And if I add the next guy, which is 1 divided by 6 factorial, now I'm accurate to 2 decimal points. Now I'm 1.71. So here, that doesn't mean anything per se, but I do see a pattern where I didn't see a pattern in the other example. So I encourage you to think about this. I encourage you to go to a calculator and experiment with both of these partial sums. And you're going to see one patterns and the other doesn't. Okay, so does anybody have a question? Okay, so that's not mathematical proof, that's not evidence, so we need evidence. And so what we're going to do to verify this, so to verify this and other results about series, we state and prove theorems. That's what we do. We need theoretical results to guarantee something is true or false. We need theoretical results that guarantee that when we go to the computer and do experiments numerically, that the computer is not lying to us, or it is lying to us. I like this. Look how my cup disappears in the oceans, but then it doesn't disappear in front of me. It's like magic. Or maybe we don't like the ocean. Maybe we will go somewhere different. Maybe we'll go to San Francisco. Ooh. Maybe we'll go to outer space. There we go. This is what I like to see. We're in outer space. So we don't state and proof theorems. We state and prove theorems.
I was going to say something, but I figured if we were using ain't, don't matter at this point.
That's right. Okay, so these theorems are called convergence test. All right, so there's a few of them, and we're going to start with a couple right now, and then we'll pick up a couple more next time, and then a couple more the time after that. That's just how we operate here in La La Land. Okay, so some of this stuff is technical, but it's worth us sort of going over, because sometimes it's nice to do these technical things. You get a little insight to what more advanced mathematics is all about. And then we'll also obviously do examples where we can show you how all this stuff can be applied to particular problems. So So the first theorem is called, creatively enough, the divergence test. Now, you're going to say, well, you just called them convergence test. Yes, the divergence test is a type of convergence test. So I know that seems like some weird English language abuse, but that is nonetheless a test. So it can be stated in two ways. So actually, let me go back to the previous slide. I don't need a colon there. So let's write it like this. Oh no, wrong button, oh lady. So that's a period, and then so it can be stated in two equivalent ways. One way you can say it, which is the easy way to prove it. The first way is if something converges, if this guy converges, then the terms go to zero. So there's some logic hiding in here. And the second equivalent way to state it, which is a little easier to use, if the limit as k goes to infinity of a sub k, if this guy is not zero, then the series diverges. Now, I don't know how much logic any of you have had. Perhaps some of you have taken a class where you did truth tables before. I don't know. Many of you will if you have to take programming classes. You'll study things called propositional logic, where you have these if-then statements. Maybe some of you have seen that. But that is the language in which mathematics is written. That is the formalities of it. You'll notice that how these are written. If something is true, then something must follow. If the hypothesis is this, then the conclusion is that. So these two statements are what we say logically equivalent. So one way is to write it in terms of convergence, and the other way is to write it in terms of divergence. Does anybody have a question about this statement before we show how it works? Okay, so we give you, so if any of you are interested in some extra credit on the next homework, prove this. It's not that difficult. It's a few lines, but see if you can practice proving something logically sound. Okay, so let's look at how to use it. So examples. So the first one, let's take this series. The series k goes from 1 to infinity of, say, 2k divided by 3k plus 1. This series, which is 2/4. When k is 1, you get 2/4, plus when k is 2, you get 4/7. When k is 3, you get 6/10. This series diverges. Why? Well, we know already why. The divergence test says it's going to diverge because its terms ain't going to 0. So more specifically, what we're saying is if you take the limit of the terms, take this limit, which is a limit you studied way back in Calc 1, even maybe before, you know this limit is 2/3, which is clearly not 0. So that is how you write this up. Anybody have a question about this? Okay, let's look at another example. So let's take this limit, which we looked at before. This guy, which is 1 plus 1/2 plus 1/3 plus 1/4. This guy cannot be analyzed by the divergence test. And so then you're going to say, why? Why can't it be analyzed by the divergence test? Well, that's quite simple. Note so even though this limit of the terms, even though this guy is equal to 0, we can't conclude the series converges. We just can't. Again, if you go back to the previous 2 slides, if you look at the logic doesn't say if the terms go to 0, something happens. That's not what the theorem says. Read the logic carefully. The logic says if it doesn't go to 0, then we diverge. It doesn't say if we go to 0, then we converge. So in math, we call these necessary versus sufficient conditions. So the logic here is very, very technical. I would encourage that you try to understand what these sentences mean and think about a more non-math version of this statement. A good way to think about it is the following. So ponder this. Suppose, excuse me. Holy hell, I'm dying. I don't know what happened. All right, so think of it this way. Suppose I wrote on the syllabus, if you get an A on homework 10, you get an A in the course. Now, suppose you get an A in the course. Is it 100% sure that you got an A on homework 10? Well, not necessarily. You getting an A in the course doesn't mean you got an A on homework 10. All that sentence in the syllabus guarantees is it guarantees if you do homework 10 at a level of A, you get an A in the course. So think about that. Think about hypothesis and conclusion in these statements. Think about the if part and then the then part. So this is a good place for you guys as learners to try to really get into these more sophisticated ideas. Just because the terms go to 0, we can't conclude that the series converges. We just can't. On the flip side, if the terms don't go to 0, like in the previous example, if they don't go to 0, we definitely can conclude that you diverge. So you're going to need to think about this. I'm not pretending it's easy. It's going to take most of you, as you're all normal human beings, it's going to take you quite a while to learn this if you desire to learn it. Some of you, well, you know who you guys are. Some of you don't care.
Go back to that last slide.
Which one?
Like the one with example number 2.
This one or the example one?
Example one.
This one?
Nope. Next.
You mean
There we go.
previous one? This one?
Yeah, right there. Yep, the one you're on currently.
Yeah, okay. Do you have a question about it?
No, I just need to copy something down. All right.
Cool. Okay, so let's analyze this another way. So so what we're going to do is we're going to pretend that we are not in calculus, that we're in just like some middle school class, and we want to use our intuition. We want to use our brain. We don't want to overthink things. So what I'm going to ask you to do is I want you to, take a time machine back to when you didn't overthink things. You just used your brain. It's going to be hard to do that, but I want you to think about it. So let's use visualize it. So what I'm going to do is I'm going to draw a picture. So let's get my little arrow out. And so I'm going to have my y-axis, and I'm going to have my x-axis. And what I'm going to do is I'm going to try to draw a nice curve. It's always easier said than done. So I'm going to draw this curve. In this curve right here, friends, this is the curve y equals 1 over x. Now you might say, why would you draw that? Well, I don't know. Look at each term in my sum. It is 1 over a number. So why not, if I want to visualize it, think of something that's similar, if not the same friggin' thing. Okay, so let's remind ourselves of some points here. I'm going to try to draw this as accurate as I can to scale. That's not always the case. So let me get my purple out. And so what I want to do is I want to draw a couple things. Let's call this point. Let's remember if this point's on the curve, and I plug in 1, then it's going to spit out 1. And then if I plug in 2, so let's call this 1, let's call this 2. So if I plug in 2, it spits out a half. And then if I plug in 3, it spits out a third. And then let's go one more. If we plug in 4, spits out a fourth. Does anybody not see this sort of pattern? All right, now let's pretend that we are now going to go from math brain to visual brain. So I'm going to take another color, let's say green. I'm going to draw some lines. Draw this, I'm going to draw this. When you're like in 5th grade, you love rectangles. They're easy to handle. Everybody loves a good rectangle. And so then I'm going to draw, actually, I'm going to draw it a little more creatively. I'm going to make this rectangle. Oops. And then I'm going to make this rectangle. I'm going to make this rectangle. And then as to not make it too difficult, I'm going to finish these off with my pen. Okay, so let's think about what this picture means. If I sort of get my blue back, and I just shade this little region here, and imagine you guys are all thinking as 5th graders. If I said, whoa. Gotta love when that happens. If I said, pretend you are a 5th grader, I want to know what is a larger shape, this blue shaded region or the rectangle in green. So another way of saying that is the following. So the blue shaded region is inside the rectangle of width equals 1, height equals 1. Would anybody agree or disagree with that? I don't think any of you would disagree. If you came in and I said, where is that blue shaded region? You would say, oh, it's inside that green rectangle. Okay, so that's how we would describe it in English, but how could we describe that, not in English, but in math terms? Well, in math terms, we might write we might write that the integral from 1 to 2 of 1 over x dx, because that's the area of the blue region, we might argue that that is less than 1. So that is a very sophisticated way of writing that the blue region is less than the rectangle of area 1. Does anybody have a question? Okay, so we can deduce more from this picture. We could say, okay, well, why did you just do 1 rectangle? Why don't you do 2 rectangles or 3 rectangles? And we can, but I just thought I'd start with one. But there's no reason I couldn't have done it with 2 rectangles or 3. So let me explain what I mean by that. If I go to the next page, so in a similar manner, what do we see? We see that the integral from 1 to 2, and then the integral from 2 to 3. So if we take 2 rectangles, we get the integral from 1 to 3 of 1 over x dx is less than the area of 2 rectangles. So what are those 2 rectangles? The first one has area 1. The second one has area half. So if I go back to the previous page, you will see that the first rectangle has, let's write that down. It's very important. So the area of the rectangle is 1. Here it's 2. Excuse me, 1/2. Here it's 1/3. So if I'm talking about this rectangle, if I'm talking about this rectangle, so this is a very, very, if you, once you understand what I'm drawing, you'll see that it's quite intuitive. But you got to get to the point where you understand what I'm drawing. So the area of the first rectangle is length times width, which is 1. The next one is width 1, height 1/2, so it's 1/2. The third one, width 1, height 1/3, so it's 1/3. Now, we can reason. Someone have a question? No. Okay. So without much more work, if you just sort of think about that, instead of doing 2, but 3 rectangles or 4 rectangles or 5. So in general, the integral from 1 to n of 1 over x dx is always going to be less than 1 plus 1/2 plus 1/3 plus all the way out to 1 over n. I highly encourage you to draw the picture I drew. Draw this picture and convince yourself, if I do 3 rectangles, what do I get? If I do 4 rectangles, what do I get? If I do 5, what do I get? And you'll see that this is the correct formula down here. Does anybody have a question about this? Now, what is that thing on the right-hand side? On the right-hand side, that is nothing more than the series we're studying. At least it's partial sums. So here's the big sort of result. So we already know from the previous stuff we did, the improper integrals, oh my God, what are you playing? So if we take the limit here's what we obtain. If we take the limit, we get the integral from 1 to infinity of 1 over x dx is less than the sum k goes from 1 to infinity of 1 over k. Since we know The integral diverges. So what does that mean? Another way of saying that is it grows without bound. So if this grows without bound, the series must diverge. I mean, that's the only logical conclusion. If I have this thing and it's less than this thing, and this thing keeps growing and growing, well, if this is bigger than it, it has to go and grow as well forever and ever and ever. It cannot pattern or cannot approach a number. The limit can't exist. So this is again, a sophisticated argument. It's one that you've likely have never seen before. We are trying to get information about a series by comparing it to an integral. Why would we do that? Because we have information about that integral. We can easily show that it diverges. In fact, we did that when we studied the improper integrals. And if you don't understand what I mean by that, try to integrate it. In fact, what is that integral? We can be very, very, very specific. You can even show that the log of n is less than this sum. Excuse me, I guess I should be more specific. That's technically incorrect. If I put an n here, then it's correct. And then since the log of n goes to infinity as n goes to infinity, we conclude the series diverges. So I'm trying to give you some intuition in a few ways. I can write it as an integral, but if I actually integrate that, I get log n is less than that. Okay, so do you have a question about this? So we got two more things we want to say, and then we're going to wrap it up, and we'll give you guys plenty of practice. Okay, so what do we want you to take from this? Well, remarks. Number one, the series that we just studied this series is so special. It has a name. It is called the harmonic series. And yes, harmonic is stuff to do with what you know, harmony, harmonics before, sound. So you can Google it and read about how important it is. So that's the first remark. It's very important. Check it out. Google it. And number two, and this is where we'll end, the idea used in the proof above, and I'll put proof in quotations because we kind of left out some minor technicalities, but technically it's sound. I don't know, that sounded silly. But no, I mean, it's a good enough proof for what we care about in Calculus 1. So the idea used in this proof above can be used to motivate and prove our next test. And that's called the integral test. So what that argument showed is that we can study series by comparing them to integrals. So let's state that and then let's call it a day. And of course, we'll give you lots of practice. So here's the integral test. So you now have two tests, the divergence test and the integral test. So once again, we need to have, if we're going to study a series and we want to use an integral, we're going to need some sort of corresponding function. We've seen this a few times before. So suppose f is a continuous function. Such that, let's be very careful, a sub k is equal to f evaluated at k. So suppose f is continuous such that that's the case. And then if this integral, say from 1 to infinity of f of x dx, if this guy converges, then the series converges. So this is not the most general form of this theorem, but it's the one that we're going to use in this class. So why do I say that f has to be continuous? Well, that way we can guarantee that we can integrate it. Does anybody have a question about this? And we can even be even more technical. Let's assume that all these guys are positive. That way there's no subtleties. All right, so that's about it that we want to say today. Now we're going to give you some practice problems, and then you'll go from there. Does anybody have a question, comment, concern? So we'll do a bunch of examples tomorrow. I am going to stop recording right now, and then if you have questions, I'd be happy to answer them. Going once. Space.